Hello, welcome to Deterministic Optimization. My name is Shabir Ahmed. I'm one of the co-instructors of this course. Today's lesson is going to be about computational complexity. This is a formal method for classifying problems which are hard or difficult. So let's get started. So let's first talk about a running time of algorithms. So if I give you an instance of a particular problem P, an instance I of a problem P, and an algorithm A, we'd like to understand how much effort this particular algorithm requires to solve the particular instance. So the effort is measured as the number of steps or elementary operations, so adding numbers or multiplying numbers and so on, required by the algorithm on this particular instance. So the effort required by the algorithm, of course, depends on the size of the instance. So let's elaborate on this a little bit. So suppose our problem is to compute the scalar product of two vectors of size n. So here's a simple algorithm, a kind of a simple Python function. So we have an algorithm which says that we'd like to, this function defines the product of a, b, n, where a and b are vectors of size n, and it's going to return the scalar product. It's going to multiply a j times bj for all j in this size n and return their sum. So how much effort does it take to solve this problem, which is the problem of summing two vectors of size n? Of course, we need to multiply n numbers and then sum up the products, n products. Okay? So the effort of this algorithm scales linearly with size of n, because as n increases, if I double, then I need to sum up twice as many numbers, so the effort increases linearly. Remember this example that we saw in the previous lesson where we were enumerating the possible solutions to a project selection problem. So we were going to run through all possible solutions of 0, 1 vectors of size n. And so here's the loop that we ran through, that loop where we were running, where we checked all possible solutions. We checked the constraint, then we checked the objective function value and recorded the best one. So this is an enumeration algorithm for solving this problem. Unfortunately, as we have discussed before, the effort of this algorithm increases exponentially. Why? Because remember, if there are n decision variables, each of them taking values of 0 and 1, there are 2 to the n possibilities. And so in this set solutions, there are 2 to the n possible solutions that we have to loop through. So therefore, the effort increases exponentially. So this is an exponent, where n appears in the exponent. And this is what makes this algorithm particularly bad, because as the problem size increases, the effort of the problem of this algorithm increases very, very substantially, very, very fast. And we have discussed that for n equals to 50, we estimated that the running time of this algorithm is going to be 330 years on my laptop, which is completely infeasible. Okay, so let's talk about, so one way to kind of formally define what, formally kind of set the stage for measuring running time is to use the big O notation. So let me explain this real quickly. So let t as a function of n be the effort or running time of an algorithm on an instance of size n. Okay, so we want to understand how Tn grows with n. So we don't want to know exactly how Tn grows, but we're going to talk about in kind of growth in orders of magnitude. So that's where this big O notation comes in. So let me define what this means. So suppose I have a function f of n, which is a function of n. Now we say that Tn grows in order of f of n. So the running time grows in this order, or we in particular we say that Tn, the running time, is big O of f of n, if there are constants c and capital N, such that for n large enough, for large values of n, the running time is always going to be bounded above by some constant multiple of this function. Okay, so this is what this big O of n means. So let's talk about. So let me give you an example. So here I have a function. So suppose the running time scales, of a problem with size n goes in this order: 3n squared plus 2n plus 10. Now we say that this expression, this function t of n, is order n squared. Why is that? So of course, so now I have to show that the leading term is n squared here. So we know that. So let me write this down. So 3n squared plus 2n plus 10 is less than, of course, 3n squared plus 2n squared plus 10n square whenever n is greater than or equals to 1, which is equals to 15n square, right? So now we have a constant, which is the constant c, and we know that as n is greater than 1, so this grows at most at a rate of n squared, right? So in other words, this leading term kind of tells me the growth rate. So here's some words that we use. So for example, if the running time or some function is a constant, we say it's O of 1. So in fact, as n changes, it does not change, right? We say that it's logarithmic, it grows logarithmically, or we say it's O log of n. If it is, if it grows as a logarithmic function of n, we say it's polylogarithmic. If it is log of n to the power c, we say it's linear. If it grows as a linear function, it's quadratic. We say it's n squared. If it is polynomial, we say it's n to the power c, where c is some exponent, some integer. For example, here, this is a polynomial function. And we say it is exponential if it is c to the n, like we said, when it was 2 to the n. So as we'll see shortly, so we were interested in algorithms where the running time grows polynomially or less, right? So exponential algorithms are hard because they take a long time. So note that the effort in the previous examples not only depend on n, but also depend on the size of the numbers, because since multiplying two large numbers require more work than multiplying two small numbers. So although we were talking about sizes as n only, but of course, computers work with numbers in finite precision, so we can only consider rational problem data. So we can assume that all the numbers are integers for simplicity. And so the computers work with binary or bit representation of numbers. So the size that an instance requires is the total space required by the problem data. So for example, when we're trying to solve the product problem, when we're trying to sum up when we're trying to come up with the product of two vectors, what is the size of an instance? Well, each vector involves n integers, where the integers have a maximum size of u. So to represent an integer of size u, you are going to require log u bits. Remember, we're going to represent a number in binary, so at most log u bits. So the total space required is 2n times log u. So this is going to be our kind of size representation, but sometimes, we don't worry about the numbers too much. Sometimes we're just going to call about n, the number of data involved. Okay. So we say that an algorithm is polynomial time if its running time or its effort, Tn, as a function of the size of the instance, is order nk for some k. Polynomial time algorithms are efficient, and problems for which such algorithms exist are deemed easy. So here is a little plot where we say, on the x-axis is the size, and on the y-axis is the running time or the growth or the complexity. And like, for example, if we have a linear algorithm, the green line, so it grows linearly. If we have a polynomial algorithm, like the blue line, it grows kind of in a polynomial factor. On the other hand, if you have an exponential algorithm, like 2 to the n, it grows very fast. We could even have a super exponential algorithm where the running time is order factorial n factorial, and that goes much faster. So those are not good algorithms. Those are kind of exponential time algorithms. So now, of course, not all problems admit or have fast algorithms like polynomial time algorithms, and that brings us to classifying problems. So problems are classified. We can say a problem class P. These are the set of all problems for which can be solved in polynomial time. So these are what we call easy problems. So these are problems for which we know a fast or a polynomial time algorithm. Problem class NP. This does not mean that this cannot be solved in polynomial time. What this means is that these are the set of all problems for which a given solution can be verified or checked in polynomial time. I will elaborate on this in a minute. So of course, if a problem can be solved in polynomial time, then we can verify whether a given solution is correct or not in polynomial time also. So the set of problems which can be solved in polynomial time also belongs to the set NP. So what do I mean by verification? So let's talk about this particular problem. So this is called the partition problem. So here we are given a set of integers, a1 through an. So our goal is to find a subset of this of the index set 1 through n, by which we can partition these integers into two parts, such that the sum of the integers in one part, j belonging to n, and the sum of the integers in the other part, j not belonging to n, are equal. So unfortunately, we do not know whether we can solve this problem in polynomial time. In other words, if I give you a set of integers, n integers, whether you can solve this problem using an algorithm whose running time grows polynomially with respect to n, we don't know. We don't know of such an algorithm. However, if I give you a particular set S, you can easily check if it is a solution. So if I give you a set, then you can just sum up the numbers in S and sum of the numbers not in S and check whether they're equal. So this is what I mean by the verification problem, right? So here we can verify easily whether a given set or a given solution is a solution or not. So this problem is not known to be in P, but it is known to be in NP because we can verify a given solution easily. So a $1 million question is whether P is equal to NP. So I say it's a $1 million problem because there is actually a prize for which if one can prove that P is equal to NP or prove that it is false, you're going to earn $1 million. Now this conjecture, the P equals to NP conjecture, is widely believed to be false, but a formal proof is not known. Now within the set of problems in NP, there is a set of problems such that every problem in NP can be easily converted to a problem in this set, right? So these problems are called NP complete. Now, if you can show that one of these problems in the NP complete set is in P, then we know that P is equal to NP. Why? Because since every problem in NP can be converted to this one of the problems in NP complete set, so therefore, if we can show that one of these problems is in P, then we can solve all the problems in NP. Easily in polynomial time. So this kind of Venn diagram shows us the classification. So we have the problems which are NP. These are problems for which a given solution can be verified easily in polynomial time. Within this subset, we have the set of problems P which can be solved in polynomial time. And then we have the set which are called NP complete. And we do not know whether these are kind of equal to each other. So I've just written them as these are kind of separate from P, for which any problem in NP can be converted to a problem here. So if we can show that an element here belongs to P, then this entire set belongs to P. Now, for some problems, it is not easy to check whether a given solution is correct. So here is an example. So this is an optimization problem where this is the project selection problem, which we call the knapsack problem. Now, if I give you a solution to this problem, I can of course check whether it is feasible or not, but we do not know if there is another solution, feasible solution, which objective function value is better than this. So in fact, checking whether a given solution is optimal is hard as solving the original problem. So this problem is not in NP, and this is the case with most difficult optimization problems. All right, so here we do not know whether a given solution is optimal or not, because checking whether a given solution is optimal is as hard as solving the problem. And unfortunately, this is the case with most of the difficult optimization problems. So there are some problems which are not in NP. And so these problems are known as the NP hard problems. So a problem is NP hard if an algorithm for it can be converted to one for solving any problem in NP. So an NP hard problem may not be in NP. All NP complete problems are NP hard, but not vice versa, because we do not know the NP hard problems are not in NP. And NP hard means that this problem is at least as hard as any problem in NP. So sorry, there's a lot of repetition of the words, but let me just kind of illustrate with this little Venn diagram again. So here I'm trying to illustrate, suppose that P is not equal to NP. Remember that we do not know. Suppose we conjecture that P is not equal to NP. So then of course, we have the class of NP problems, within which we have the class of P problems for which we know the polynomial time problems, polynomial time algorithms. And then there's some of NP complete problems for which we can take any NP problem and reduce it to this or convert to this. And then there are these NP hard problems. For NP hard problems, we do not know whether they are in NP or not. So they could be in NP or they could be outside NP, because it's hard to verify in polynomial time. So we do not know whether there exists a polynomial time algorithm to verify a given solution. But we know that every problem in here in NP could be converted to an NP hard problem, right? So this is when P is not equal to NP. Now if P is equal to NP, then we know that this all this distinction between these sets within the NP class kind of goes away, because any problem that can be solved in polynomial time, any NP complete problem, if it can be solved in polynomial time, then we can solve all the NP problems. So therefore P is equals to NP is equals to NP complete. But there could be some problems which are not in NP, the NP hard problems, for which we still do not know. Okay, so this is what the depending upon whether P is equals to NP or P is not equals to NP, how the problem classification changes. So now linear programming and many important class of convex optimization problems, such as conic programming and semi-definite programming, are known to be NP, for which for these problems we know polynomial time algorithms. Unfortunately, discrete optimization problems or integer programming problems are NP hard. We do not know polynomial time algorithms for these problems, and we do not know how to verify a given solution in polynomial time. Now, it is widely believed that there is little hope of finding a polynomial time algorithm for discrete optimization problems. So in some sense, the enumeration algorithm that we talked about is probably the best we can do in the worst case. But of course, not all problems are as hard as the worst case, so we will try to come up with something a little bit smarter, and we'll talk about those later on. So let's summarize our discussion of problem classification. So we said that an algorithm is polynomial time if its running time grows at a rate which is no more than a polynomial function of the instance size. Problems for which polynomial time algorithms are known are easy problems. And so that allows us to classify problems into P, NP, NP complete, and NP hard. Unfortunately, discrete optimization problems are NP hard. For with these problems, we do not know polynomial time algorithms for solving them or verifying a given solution. All right, so we will pick up in the next lesson.